right. Hello, everyone. Quick sound check. Oh, I didn't do my intro music today. Forgot about that. Quick sound check. Can I get on the chat that you hear me? It's all good. All right, cool. We got one response. All right, so running here at about a minute. We'll get started. Good morning. All right, yeah, I guess good morning. All right, let's just go ahead and get started as we're at about that time. I'm trying to really keep to time with these lectures. All right, so today's lecture is on elementary sorts, but I know, or elementary sorting. Basically, we're going to discuss at least 3 algorithms, potentially 4, depending on what time allows, that we would consider elementary sorting. You might have already been familiar or seen some of those before. But these are particularly important to talk about, and we're also going to be discussing kind of some micro optimizations for these algorithms that you can take into account if you were to implement these algorithms from scratch. Oftentimes, we don't have to implement sorting algorithms from scratch because every library has their own sorting algorithms. So we just in fact, in your projects, you're just going to be using STL sort for the most part. But it is important to understand sorting because it comes up almost everywhere in terms of whatever go off the industry, and you're going to end up having to sort some sort of information. And so it's important to know the pros and cons of each one of the algorithms that are available for sorting. And in fact, even elementary sorts might come in handy in a couple of practical instances, as we're going to talk about later today. All right, but before we do that, I know I owe you kind of the whole, let me go back, union find example that I would go over. So if you recall, there are a couple of examples for the different types of union find that one can do. Again, discuss all of this in detail in the last lecture, but did not manage to get through the last example of doing the path compression. And I think there was probably some confusion with the next to last example, which was doing hierarchical representatives. So let's do one real quick. I think I figured out where I might have introduced the confusion. So let me just do it again. So if you recall, it starts out with everybody, each one of the elements or the items, whatever you want to call them, as their own representative, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And if you recall, doing a join implies, that's supposed to be the word join right there, implies that you're doing a find on each one of the arguments to the join. You're going to do a find, and then a union. That's what we mean by join. All right, so first step is we do join of 1 and 6, which would mean that we do a find on 1, which gives me 1, so its own representative, and do a find on 6. So its own representative, determine that they are in different sets because they have different representatives, and now I want a union. And we said that by convention in these examples, we're going to pick the representative of the first argument that gets passed to the join, which in this case is 1. So therefore, we said the representative of 6 to be, that's supposed to be a 1. This is terrible. See if I can quickly fix it. 1. Okay. Then join of 1 and 8, same deal. You do a find on 1, you get 1. You get a find on 8, you get 8. End up deciding that when you union, you're just going to set the representative of 8 to 1. And then same deal here. Join 1 and 3. Set the representative of 3 to 1 by the same rules that we've been talking about. Now here is where I might have introduced some confusion due to the type of annotation that I did on the table above. When I join a 5 and 6, what's going to happen? I'm going to do a find on 5 and determine its own representative. Then do a find on 6 and see that its representative is 1. So what this will do is that now 1 is going to be repped by 5. Okay. So I think in the previous lecture I said this, but then what I scratched was the 1 from the representative of 6 and scratched that to make it a 5, and that introduced confusion when I was trying to identify which of the items belong to which set, which in the end it turns out everybody ends up in the same set as we wanted. So now join of 4 and 7 is pretty easy. It's the same situation because each one is their own representative. So I just picked this to be 4. And join of 4 and 2, same deal. 4 would be the representative of 2 now. And now we join 5 and 4. So now what's going to happen is same deal, each their own representative. So this is 5. Okay. Now, if and this is where it's you'll see that the find operation is going to be linear time, because if we now wanted to find out who is in what set, right? Then our find operation is linear time in that it's trying to find a representative of each element, and you can go back in the path multiple times, right? So, for example, if I wanted to see the representative of 1, that's 5, so I'm going to circle everything as blue for the items that belong to the current set, right? And so then if I do a find on 2, that gives me 4, and then 4 gives me 5. So now I see that they belong to the same set as 1. So 2 is indeed in the same set just by following the representative of the representative of the representative. Then if I do a find on 3, then that gives me 1. 1 gets me to 5, and then 5 gets me to itself, right? So like I'll write it like this. If I do a find, so F for find on 3, right? That's first going to give me 1, but then I need to follow the 1, and that gives me the 5. And then I look at the 5, and that just gives me itself. So I know that 5 is the actual representative. All right, so 3 is also in the same set. That's represented by 5. Then find on 4, that immediately tells me that it belongs to set 5, 5 on 5. Then check 6, that gives me 1, which then gives me 5, so it also in the same set. And then 7 gives me 4, which then gives me 5. So it's also in the same set. And then finally 8 gives me 1, which then gives me 5. And then, boom, everybody's in the same final set. Okay. Shouldn't it be 6 that gets replaced? No, because you're going to do a find and see the representative is 1. So you're going to update the representative of 1 to be 5. Oh, my apologies. Sorry about that. Shouldn't it be, okay, I see. So you don't change every one of the yes, you don't change every one of the representatives. That is the key. That's why union is a much quicker operation, but then the find, you shifted the burden to the find, right? Because you don't update everything, but then the find will have to weed its way into finding what the correct representative is. Okay. All right, but then that's not ideal. What we would want is something that's even more performant than that. And that's when we talked about path compression, where what we're effectively doing is that now the find operation is not just read-only, but it's also going to be an update operation. So when we do a find and we've realized that, hey, I have to do multiple steps to get to the correct representative, I'm going to actually update the representative immediately after doing the find, such that next time I do a find on the same item, it doesn't have to do multiple jumps to find the correct representative. The representative would have already been updated to what it is. Okay, so that's what the example that we're going to talk about. And when we do that operation, because when you're updating during the find operation, when you're updating the representative, it means that you won't have to update the representative every time. So you're able to amortize that operation. So only once in a while would you have to spend the time to make the proper updates. But once you did the update, then it's all done. And so you wouldn't have to spend that time updating again throughout the operation. So you amortize it. And people have done analysis specifically. Well, I don't recall who did the analysis, but it comes up with the inverse Ackermann function, which it's an asymptotic function, but its limit is 5, so it's just as much as constant time. All right, so here is the union find example using path compression. So again, we initialize everything to 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, join of 2 and 4, right? So that would mean that we would make the representative of 4 is now going to be 2. Same rules that we had for the previous example. Join of 1 and 2 means that now 2 is going to be represented by 1. Okay. 5 and 7 means now 7 is going to be represented by 5. 5 and 6 means now that 6 is going to be represented by 5. So nothing much has happened, because every time I'm doing a find on the arguments to the join, I'm finding that they're their own representatives. So the update is pretty simple, and the find doesn't have to do extra work with so far. So now step 5 here, we're doing a join of 8 and 5. And same deal, when we do a find on 8, we get 8. When we do a find on 5, we just get 5. So that's a pretty easy update to set the representative of 5 to be 8. All right, so really nothing extraordinary has happened here, different from the previous example. But here we go, and how this is going to be different from before. Okay. So remember that now the find operation is the one that's going to actually be doing the updating. So let's say that we do, again, F for find, and we do a find on 4, right? If we do that right now, we get 2, that's its current representative. And then we check 2 and see that it has representative 1. And then go to 1 and see that it's its own representative. So it's done. This would be saying that the actual representative for 4 is 1. Okay, but traditionally the find operation would end there at finding the correct representative. But as we're saying with path compression, after you do this, what you're going to do is say, well, now that I know what the correct representative is, I might as well set the actual representative to be 1, right? So I based that at that point. We now set this to 1. Okay. And then we do, let me use a different color. Then we do a find on 8 to find out, all right. Apologies, is it back? Is it back? Yes, my software is saying that we're back. Can yay! All right. Can somebody in the chat give me a quick where did it freeze? Should I? I guess I should restart the find on 7. Let me just do that. All right, so yeah, I might have written find on 8, which is bad. I meant to do find on 7, which is what we're looking to join. Okay, so instead of find on 8, we would do find on 7. Again, that's what we're actually joining here. Okay, but that gives me a representative of 8, right? Which then I look at, and it has a oh, sorry. Again, this is because I need to redo the entire example. This is confusing. Need to undo a couple of things here. This is 5. Okay. All right, so start again. Find on 7, which gives me 5, which then gives me 8, right? And then 8 in itself. So that tells me that 8 is the actual representative. Okay. So I found the correct representative. So now the find itself would update and say like, okay, no longer am I going to have to go through 5 to find 8. I'm just going straight up to 8. Okay. So then what the update is here is the representative 7 now becomes 8 directly. Oh no, the drawings are frozen. Oh, dang it. Let me see if... Yeah, you're right. It is frozen. Let me see if it's a matter. All right, 1 second. Bear with me, everyone. I might try something here that might disconnect me for a second. Okay, Google, play Matrix and Future Bound. Just give you some music there until I figure this out. All right. I think. Can somebody tell me whether it's all good now? I'm seeing. Oh yeah. Sorry about that. Okay, Google, stop. So I have my Google Assistant here, not to do a promo, but we are using YouTube anyway. So I mean, whatever promo. We're already giving plenty of promo to Google with YouTube. All right. All right. Sorry about that. Let's start this all over again, I guess, because there's really no way to do it. That leaves us less time for sorting algorithms, but we'll see what we can do with that. All right. So start again. Basically, everything is set to its own representative. Join of 2 and 4, that means this gets changed to 2. Join of 1 and 2 means that this gets changed to 1. Join of 5 and 7 means that this gets changed to 5. 5 and 6 means this gets changed to 5 as well. 8 and 5 means that this gets changed to 8. Okay? All right. Let's see. Let me do a quick check. Everybody good till now, and you can see the stream, and you saw all the previous steps. Let me get a quick chat check. All right, because this is like up until now, all the steps are real easy because nothing fancy happens. But with this last step is when all the magic happens. Basically, what I need to do is a find on 4. If we go by that table, if we do a find on 4, that'll take me to 2, which then takes me to 1 to find that it's its own representative. So therefore, the representative of 4 is 1. All good there. But now, because the find operation will also update, it will say, oh, if I know the representative is 1, I might as well just make the update on the table above to say that if I do a find on 4, it should get me directly to 1, not having to go through 2. So therefore, the update here is 1 on the table. Okay? And then as we do a find on 7, that gets me to 5, which then gets me to 8. Apologies for earlier saying find on 8. That was completely wrong because we're doing a join with 7. So it's a find on 7 that gets me to 5, which then gives me to 8 to find that that's its own representative. So the actual representative of 7 is 8. Okay? But again, what we will do is, all right, well, if I know that 8 is the representative of 7, I might as well update the table right then and there. So I don't have to go through 5 and then make the change right there. Okay. So now we have shifted the burden to find, right? In fact, it's not, the find not only has to traverse a path like before, but it also has to do an update. But because we only have to do this update once in a while, because once you updated the representative, chances are you don't have to update it again throughout the lifetime of the union find. So amortized time gives you a constant for the find operation, even though it's incurring the burden of the update. Okay, and in fact, both operations, the union and the find, follow this Ackermann function, inverse Ackermann function on n, which is again effectively constant time. All right, cool. So hopefully, after all that trouble, we've cleared that up. Why doesn't the 7 rep become 5? Because why doesn't the 7 rep become 1? It does not, because its actual rep is 8, right? If I did a find on 7, that would have given me 5, and then if I did a 5, it will give me 8. Okay. All right, but let's move on to elementary sorts. Again, feel free to come to lecture office hours, so we can take our time in going over these examples if you would like. Just making sure, because we're at almost 12:30. So yeah, let's get going with elementary sorts. As I said, very important topic to know in detail. There will be a bunch of sorting algorithms that we will be discussing between today and actually the next 2 lectures. So this lecture would mostly be dedicated to elementary sorts. That is your bubble sort, selection sort, insertion sort. If we get to it today, we'll discuss counting sort. Counting sort is very similar to bucket sort, but so it's a variant of bucket sort, or bucket sort is a variant of counting sort, depending on how you look at it. Very related, but there is a slight difference. Then there's your high performance sorts, which is quick sort, merge sort, and heap sort. Heap sort we already discussed when we were talking about heaps. So we won't discuss it again, but we will have 1 lecture dedicated to quick sort and 1 lecture dedicated to merge sort. Radix sort is also a very interesting algorithm. We will not discuss it in detail because we won't have time, but we encourage you to look it up. Very interesting algorithm, and I usually say a bit more about radix sort, but in the interest of time and because we don't really cover it, I'll just skip it. I'll let you look it up. All right, so elementary sorts do not mean that they are useless, okay? In fact, we will discuss situations in which some elementary sorts are quite useful, okay? They basically illustrate how to approach the problem, how to compare multiple solutions, how to look at code in order to optimize. Some of them are micro optimizations that we'll talk about today, but again, it's the whole approach of thinking optimally and how to squeeze performance out of your algorithm is of particular importance. And oftentimes we do combine elementary sorts with your more sophisticated sorts, right? In fact, I think in 1 lecture I mentioned intro sort, intro sort is kind of basically you make a decision of what is the best sort to use. Sometimes one of the best sorts to use, it's actually one of these elementary sorts, and I'll talk about which one that is and when. Okay. So which containers can be sorted? Yes, I mean, you can sort anything really, you given the right tools, but as far as our lectures are concerned, we have arrays and we have linked lists. Those are the 2 types of representations that we have discussed. And while we will consider both, we're going to start with arrays. Okay. Now, as you're going to see, some of the tasks that are involved in our sorting algorithms are going to be better suited for arrays, while others are going to be more adequate for linked lists. Okay. And we'll make sure to point that out. But keep that in mind. Really, for today, we're definitely only going to be looking at arrays. Okay. Now, STL has a sorting algorithm that you can use by doing a pound include algorithm. Okay, so there is an actual library called algorithm, contains sort, and it sorts on ranges. So you have a begin iterator and an end iterator. Okay, so in this lecture, just to reduce, honestly, in terms of software engineering, as we've mentioned in the last lecture, the proper way would be to implement any sorting would be to rely on iterators. However, just to make the code more compact and easier to understand in these lectures, we're going to be using just straight up integer arrays, right? As opposed to, and so we're using integers as pointers to elements in the array, but not iterators in themselves, okay? So what we would do is call, say, some sorting algorithm, which say bubble sort, which we're calling bubble here, and then pass it the, let's call it left integer for where the range starts, and then the right integer for where the range ends. Okay, so that's analogous to passing the begin and end iterators. Okay. So a good exercise would be take everything that we discuss in lecture and try to re-implement using iterators, because if you care about software engineering, that would be the proper way. Okay. All right. Now let's talk about some categories for our sorting algorithms. You have internal sort, which would mean that all the items that you're looking to sort, or elements that you're looking to sort, you can fit them all in memory, right? And that's going to be the most often situation that you're basically going to be doing in your projects. And so, which is why something like STL sort works fine. Okay, so internal sort just means that you can fit everything in memory, and you have random access to each one of the items. Okay. Indirect sort means that, hey, I cannot fit the actual data that I'm looking to sort, but maybe each one of those items has an index that I can use to sort over. And so what I load in memory is all these indices, sort them, and then kind of after the fact, I join each one of the indices with their respective data in the correct sorted order. Okay. So you're really sorting indices rather than the items themselves. And then lastly, there's external sort, which is you basically have way too many items altogether. You just can't fit it in memory. And actually, external sorts, we really in the industry did not rely much on external sorts, because most of the time we could fit our data in memory. And if we ran out of memory, we just order servers with larger amounts of memory. But at some point, especially in the mid-2000s, as the advent of big data, where we're really storing like terabytes of data to disk, then it was apparent that it was not as easy to load everything in memory. So now external sorts are particularly popular, and as anybody knows about Hadoop and big data, basically when you do sorting in Hadoop, it's using an external sort. And more specifically, it's using merge sort, which we're going to discuss in 2 lectures. All right, so an external sort, what you'll have to do is, because you can't fit everything in memory at the same time, then you'll just do chunks or blocks of memory that you load into RAM, and then sort that. And of course, you have to account for the fact that there's remaining data that you haven't sorted, and so how do you deal with that? It's not a trivial question, but that's where merge sort comes in quite handy. All right. So in discussing any sorting algorithm, you have several building blocks. You have the less than operator, which is what we're going to use to compare. You have the random access, which is just a square bracket operator. You have a swap operation, which you've seen many times. Then you have whatever you call your sorting algorithm. And then you're going to have a main function that you're going to use to test your sorting, which is just going to consist of filling a vector or an array with a bunch of random values, passing it to your sort algorithm, and then making sure that the output is as expected. So this is what we encourage you to do for whenever you're testing anything, really, specifically with Project 2, as you're going to be implementing the different priority queues for your part B of the project. This is a similar approach that you might take, right? Just create a bunch of random variables inside of an array, push all of them into your heap, and then make sure everything comes out in the appropriate order. So, and a big assumption, not a big assumption, but what we're going to have to do for simplicity, similar to when we were discussing heaps, where we assume we were always dealing with a max heap, we're going to assume that we're always going to be sorting in ascending order. Okay. All right, so a quick exercise that we usually do in lecture is that you write your own swap function. I mean, it's pretty simple, and we don't, interest of time, we'll kind of skip it, straight up give you a solution, which I'll also let you browse at your own time because it's not terribly complicated. You've probably already implemented something like this in previous courses, like 183 or 280. Maybe what you might not have done before is use a templated function like this one. Okay, so take a look at that. But swap is, just what it implies. You would swap two items inside of an array. Okay. Okay. Now, one thing is there is a swap utility function in STL. Okay. Which is highly optimized. So you definitely want to rely on that as you in your projects. Now, for whenever we implement a sorting algorithm, we're looking for specific properties of interest. Okay, and one of those is, of course, how fast is the algorithm, which is asymptotic complexity, and we determine that in terms of number of comparisons. And depending on what the algorithm is, we might consider number of swaps. Okay, because there's some sorting algorithms that will use swaps, others will not. Okay? But all sorting algorithms are definitely going to use comparisons, right? So number of comparisons is always important. And there's going to be worst case analysis that we're going to be interested in. And when we talk about quicksort specifically, we're going to talk about average case analysis, which I'm sure you're all dying to look at because we haven't really given you examples on when this average case analysis is useful, right? And best case analysis is almost never useful. I mean, we will talk about it, but a robust analysis is never or almost never interesting. So the main two that we'll be talking about is worst case and average case analysis. For elementary sorts, we really concentrate more on worst case. When we talk about quicksort, we'll talk about average case. And then memory efficiency is also particularly important. Sorting in place means that you would not use any extra memory, or any extra memory that you use is constant, right, throughout the lifetime of the algorithm. Then you can sort in place with recursion. Okay, so here there are things to consider with regards to whether it's tail recursive or not. Sort in place but have pointers or indices. Same deal. Some sorts might need at least a linear number of extra memory, and we'll talk about what that algorithm is. In fact, I'll save you. This is really merge sort is the one that is going to need extra memory. Save you the suspense. Okay. Yeah, the issue with having to use pointers is that, of course, you have an additional end pointers or indices that you're going to need in order to do. Oops, my apologies. So also not ideal, but it's not as bad as requiring omega n extra memory. Because assuming that the pointers or indices are much smaller than duplicating the data, if you will, by creating the extra memory. Stability. This one is something that you might have not heard of before. So with sorting algorithms, we care about the stability. And here what we mean is that if two items have the same key value that's the value that you're going to compare to determine the sorting order. So if they're equal, if their key is equal, the order in which they're going to come out of the sorting algorithm is the same order that they had before. Okay, and it's going to be relative order because presumably you might have moved all the other items that are not equal. You're going to have moved them about, and even you might have moved those same items themselves in the output, but the order in which they come out is the same order in which they came in. Okay, so let's look at an example of that. Kind of more complicated to explain than it actually is. So let's look at an example. You have input, which are names, and then you have a last name and a first name. And what you want to do is sort by last name. Okay, so we want to sort by last name only, which means that you have, in this input, you have Charlie Sheen, or Shin Charlie, and then Shin Martin. So with regards to the keys that I'm comparing, which is really just Sheen, right? Those items are in fact considered equal, right? As far as the sorting algorithm goes, because all we're looking at is the Sheen name. So that would mean that after I run my sorting algorithm, the output's going to be stable if the same order that I had for Charlie Sheen and Martin Sheen is the same order that I see in the output, right? So here, Charlie Sheen did indeed come before Martin Sheen, right? So that is a stable output. But if I'm not able to say that this is going to happen 100% of the time I run my sorting algorithm, then my algorithm is unstable, right? Like if there is a chance that, for example, Martin Sheen might come out first or before Charlie Sheen, then I say that my sorting algorithm is unstable, right? I don't have that particular guarantee. And again, we're gonna talk about which of these sorting algorithms are stable versus unstable. Okay. All right. So another type or category that we use to describe sorting algorithms is adaptive versus non-adaptive. The distinction is going to be that in a non-adaptive sort, it does not take into account, or has no logic that would behave differently if the input data had any sort of order. In essence, if your input data is almost sorted, you can imagine you can have a sorting algorithm that, because the input is, call it almost sorted, then it might behave differently than if the data is just completely random. Okay? So a non-adaptive sort is that the algorithm would behave no matter whether the data in the input is almost sorted versus completely random. Whereas an adaptive algorithm would be able to perform better if the data is, say, almost sorted, right? And later on, we're going to describe or have a precise definition of what we would mean by almost sorted, right? But if you can imagine, right, some array that has the values 1, 2, 4, 3, 5 is almost sorted, right? All I would need to do is swap these two values to get a sorted output, and that is almost sorted, whereas if I had 2, 1, 4, 3, 5, that's almost completely random. Okay? And of course, that's kind of very wishy-washy way of describing almost sorting, but again, we're going to explicitly describe later on. Okay? And here's our first elementary sort. Okay? Bubble sort. So this one you might have heard of, probably. You might have even seen it before. To me, bubble sort is interesting because if I, or at least I feel that if I was ever given the task, implement a sorting algorithm, and I knew nothing about sorting, I honestly don't know how I would have come up with bubble sort. And it's an algorithm that's not very performant. The way that it conceptually works, right? So we have an outer loop, and then we have an inner loop. The outer loop is going to find the minimum item, okay, that should be placed in its rightful position, right? Because again, we're assuming that we're sorting ascending. So the first element should be the minimum element in the array. Okay. So basically, what I do is find minimum item on first pass by comparing adjacent items and swap item all the way to the left, right? So first iteration would find the minimum element and use the inner loop to basically swap to right position. Second pass, we'll do the same thing, okay? But for the next to last position, or sorry, the second position, my apologies. So on and so forth. So let's look at an example here. So let's say that this is our input, 4, 2, 5, 1, 3. The first pass, right, of this outer loop, okay, we'll take the smallest item, or the minimum for the array, and the inner loop would take care to swap, okay, all the way down to get it to the correct position. Okay, then pass 2 would do the same thing for 2, which is really just one swap. Okay. Then do the same thing for pass 3. But in fact, if you look at it, even though it's already sorted, we need another pass to determine that there's no additional swaps that are going to be needed, right? And you're only going to swap if, the array, the adjacent item that you're comparing against is less than, because otherwise you wouldn't want to swap, because if it's not less than, it would not get to its right position. So you only want to swap if it's less than. So you have this extra pass, right, that you don't, it's largely unneeded. So can anybody suggest a way to improve this, right? Noticing the fact that our algorithm relies on swaps, okay? Can anybody point a way to improve this bubble sort? Basically by eliminating this last pass. So what I want is to not have to iterate one more time. Anybody want to suggest what to do? Right, that would be it, right? If two elements haven't changed since you last checked them, or in fact, it's simpler than that. If you can check whether you've done a swap. If you've done no swaps, then that means that you don't need to do another iteration because there's nothing to swap. So this is how we arrive from a non-adaptive bubble sort to an adaptive bubble sort. Basically, you have a Boolean. Okay, so this is adaptive bubble sort. You have Boolean that checks whether you have incurred any swaps previously, right? So you set it to false initially, and then in the same if statement that you're doing the swap, you set that Boolean to true. If at any point you perform at least one swap, then you will have to incur that extra iteration because you're not sure that everything is in its rightful place. But if you have not done any swaps, then that means that everything is sorted and you can break. Okay, so there's no need to do that very last iteration of the outer loop. Okay, and this is what we call adaptive sort, because as you can see, you've introduced logic where depending on what the current state of the array is, it might make a decision to continue sorting or not. Okay, well, in this case, we would not continue sorting based on the fact that we have done no swaps. Okay, All right, so an analysis of bubble sort would be, for the non-adaptive version, we have on the order of n squared. Of course, you have the divided by 2, but it's effectively O of n squared, right? Comparisons and swaps in worst and average cases, right? So we will not look at the analysis for average cases here. But if you were to do it, you would see that even if it was an average case, you would still do that number of comparisons. Notice here that an average case analysis would mean that our input array, we have to assume that our input array follows some particular distribution of the input, which we can say it's a uniform, is what's used often, unless there's a particular context where you know that, hey, your data and your input might follow a different distribution, okay? And by uniform distribution, it's like any element is just as likely to end up in any particular position of the random array. Okay. Then for the adaptive version, we have same deal. I mean, none of these adaptations that we're going to talk about or optimizations are going to make are going to change the asymptotic complexity of our algorithm. So O of n squared in terms of comparison swaps. Now here, because we have that Boolean, right? We have a linear number of comparisons that you would get in the best case, right? That would be, say, if you give it as input a sorted array, right? Then bubble sort is actually a bit smart in being able to detect that, right? Because you'll only run the outer loop once, determine that there's no swaps to be done, and then you can exit out early, right? So that goes to also in the as few as 0 for the best case. Okay. All right, so that's bubble sort. Of course, there's a lot more disadvantages to bubble sort. Both comparisons and swaps are, it's an n squared algorithm, and it actually performs quite poorly experimentally, especially as compared to other elementary sorting algorithms like insertion sort and selection sort, which are also n squared, but in practice are much faster than bubble sort. Okay, they're obviously not faster than, say, quicksort, which is n log n, but bubble sort is pretty bad because it, as you're going to see, it does a lot more work that it needs to in the swaps, and having to just bubble down each one of the elements to its rightful position. It's particularly wasteful. Okay. All right, any questions about bubble sort before I move on? And this I'll have to look at. I apologize for kind of rushing through things a bit, but sort of the earlier exercise, checking if sorted is too slow for doing it every single time. All right. Seems no questions on bubble sort. All right, I'll move on. Next one that we're going to talk about is selection sort. And if I feel, I guess, if I had been given the task of like, hey, implement a sorting algorithm without ever looking at any sorting algorithms, I honestly feel this is the algorithm that I would have come up with. I mean, I don't know whether that's a fact, but that's how I feel. It is, in other words, what I'm saying is, to me, selection sort is the most straightforward and the one that makes most sense, if you will, or the one that I would think about to implement. All right, so here, it's very related to bubble sort in kind of the concept that it's using, except that it's just is not wasteful about the swaps. I mean, if you had to summarize the difference between bubble sort and selection sort, it's exactly that, right? They're kind of similar in conceptually what they're doing with the outer loop and inner loop, except that selection sort is not as wasteful in terms of the number of swaps, right? The way to think about it is the outer loop goes for every position in the array. Okay, and I know, and I'm using my own words. They do not exactly match with, I guess, the name of the variables or the logic. But again, conceptually, the outer loop, think about it like I'm going to go over each position in the array, right? And then the inner loop is going to say I'm going to find the value that corresponds to that specific position that I'm currently considering. Okay. So one way to look at this is that at any point in the array, you're going to have a portion of the array that is sorted. Oops. Then you're going to have a portion of the array that's unsorted. And then you're going to have the item that you're looking at, call it I. Okay? Oh, not the item, but the position in the array that you're currently looking at would be I, right? And all you're trying to do with the inner loop, right, is find the correct value that should be placed at position I, right? So this inner loop, as you can see, it starts at I plus 1, right? So the inner loop is just saying, all right, I'm going to search the sorted portion of the array to find the correct value that should be placed at the ith position. Okay. And that to me makes a lot of sense, right? If I were trying to sort a bunch of names, that's what I would be doing, even if it was on a sheet of paper, right? So this is easy to see if in the code itself. If you look at lines 4 and 5, that's basically 4, 5, and 6, actually. Those lines of code is what you would write if I told you to write a function to compute the min of the array, right? Compute the minimum value in the array. You would write code that is very similar to lines 4, 5, and 6. Okay. But the only difference is that instead of fetching what the actual value is, what you're finding is the index of where that value is. So you remember what that index is, and then you use that index to do the single swap here. Okay. So you can see how it's, more performant than bubble sort, because bubble sort would have had, well, first, bubble sort here would start from left as well instead of I plus 1 in line 4. And also, the swap would be inside of the inner loop, right? Which is why we had, in the worst case, O of n squared number of swaps, because the swap was inside of that inner loop. But now we've taken that swap, and it's outside of the inner loop, okay? But it's still inside of the outer loop. So you can already tell that we should have on the order of linear number of swaps for this algorithm. Okay, so let's look at a quick example. Okay, so here we have the same code, same algorithm, and we have as input 4, 2, 5, 1, 3. The first pass, right? It would say like, okay, I'm looking at I equals 0. So conceptually, what it's going to do is let me find the value that corresponds to that very first position, which in this case is 1. So it does basically a min on all of this to find 1, place it there, and then I is now 1. So what the algorithm is going to do is like go find the min of what remains, which is this section of the array. So in pass 2, I would find that 2 is the actual value that gets placed. And then next time around, where I is 2, I would be looking at this section of the array, find the min to be 3. So that gets placed right there. Now I is equal to 3. which means that I'm going to be looking at this section of the array to find 4 and then 5. There's nothing else to look for. There's only one element in what remains, so I would end right there. Okay? Yeah, so pretty much like selection sort. Simple, straightforward, and not particularly wasteful like bubble sort is. Again, I don't know how anybody would come up with bubble sort. It seems like it's intentionally doing extra stuff. All right, any questions on selection sort? Quick questions before I move on. And I forgot to bring my water. Give it 30 seconds. Lag. Does the sorting range include the right index? It depends what you mean by the right index. So it does include, does the sorting range include the right? We are not sure. Isabella, if you can elaborate on that question, I'm not sure what you would mean by I'll give it a couple of seconds. While I see that, okay, yes, go ahead. Left and right. No, it goes out to right -1. Okay, I see what you mean now. Yep, got it. Yes, no, it does not include right, because you'll see that the for loops go out to right -1. Okay. Now this, you see that this, the inner loop, because it starts at I plus 1, it does need to go up to right. Okay. All right, selection sort. This is complexity. I mean, we're not really doing the complexity analysis. We're just telling you what the complexity is. Comparisons are always going to be O of n squared, right? And that, if you look at the code, if we go back to the code, you'll see that that's the number of times that I would expect to execute specifically line 5, right? And you can see that it's inside a nested for loop, so that points to n squared comparisons. Again, it would be on the order of n squared divided by 2, yada. Swaps, you get n-1 swaps in best, average case, and worst case. That's easy to tell by the fact that line 7, which is where you do the swap, that is outside of the inner loop, but inside of the outer loop, right? So this clearly is, O of n, right? Line 2 is O of n. So therefore, line 7 is going to be O of n. So that's linear number of swaps. So this version that we discussed is non-adaptive. So runtime is insensitive to input. Okay. But so now let's see what we could do to make it adaptive. Okay. Simple thing. Basically, you just check whether the min index that you're searching for is different than the current item that you're looking at, or index of the item that you're looking at, right? And all this is saying is like, don't swap if the item is already in the correct position, right? So, what this means is, by chance, if the element or item happens to be in its correct position relative to the rest of the array, then I don't need to do that swap because it's already there. Very, like, a really minimal micro optimization, but again, it now makes it adaptive because it's checking out for the cases in which, elements are already in the rightful place. right? So pretty simple, but nonetheless does make the algorithm adaptive. Okay, so for adaptive, that means that it can reduce kind of the number of comparisons. Still, again, n squared overall. Okay, everything else remains the same. Well, you can now at this point you would say that in the best case you get 0 swaps, right? So the best case is input is already sorted, so there's no swaps that you would need to make. Okay, and that means that the runtime at this point is sensitive to input. Okay, so advantages is one of them being that there's minimal copying of items, right? So this is a good choice when objects are large and copying is an expensive operation. This actually happens quite often in practice. So if the array is small enough, it actually performs quite fast, right? Of course, that's just a note after the fact, because what we're usually interested in terms of complexity is large n, right? But it is fair to say that for small n, it does behave in a fast manner. Now disadvantages, still O of n time factors theta n squared time, factors theta n squared time. While we did come up with an adaptive version of it that is somewhat sensitive to the input, I mean, really not much. So it's only slightly dependent on pre-order of the input array, so whether the array is almost sorted or not. So it really runs almost about the same on something that's already sorted versus array with all keys are equal and whether the it's randomly arranged. Okay. All right, so far we've discussed bubble sort and selection sort. They're both really asymptotically slow, but I would say selection sort is, more interesting than bubble sort. So next we're going to discuss insertion sort. Okay. But insertion sort has a lot more opportunities for tuning what it does, right? So, I mean, we fiddle a little bit with bubble sort, we fiddle a little bit with selection sort. We're going to be able to do a couple of more things with insertion sort. Okay, but let's first talk about how insertion sorts will work. And what we're going to see when we optimize insertion sort is that we're going to try to tune the inner loop, okay, quite a bit. Okay. So here is insertion sort, and this is, again, the non-adaptive version is what we're going to start with. So what you're going to do is consider elements one at a time, insert each into its proper place among those already inserted. Okay. So this might sound very similar to selection sort, but it is not. Okay. So the idea with insertion sort is similar to selection sort in that you, again, have like a sorted versus unsorted parts of the array. Okay. What insertion sort is going to do is it's going to consider whatever the sorted portion is, and it's going to consider an ever increasing size of the sorted portion. So next step, it would say like, all right, I'm going to add another element from the unsorted section to the sorted section. And by add is really just increasing the pointer to, look at the next element. And then see where this single element, where its rightful place is amongst the sorted part of the array. Okay, so remember, with selection sort, we were searching in the unsorted section of the array to see what should be the next value to place. Okay, with insertion sort, you're considering the next item and then seeing where it should fit in the sorted section of the array. Okay. So again, this is best by example. So you have your outer loop, okay? So we're not using any curly braces, so hopefully you notice that this for loop is inside of the outer loop, okay? So you have, this is our input example. In the first pass, what we're going to do is say, all right, right here, right? First pass means that I'm going to look at the next item, which is the 2, and see amongst my sorted portion, which is now a simple 2 elements, right? I'm going to see where does the 2 belong, right? So 2 is less than 4, so that means that I should swap the 2 and the 4. Okay, so that's what you get here. Okay, so now this effectively becomes my sorted portion. Okay. Oops. Let me do something here because I started kind of ahead of myself. Okay. So the input starts here. I consider my next one to be 2. Say like, oh, okay. 2 is less than 4, so therefore I perform the swap to get a result there. Now my sorted portion of the array is just the 2, right? Not the 2 and the 4, because I, haven't really checked that element yet. So I first need to say, all right, I'm going to increase the size of my sorted portion of the array to now consider 4, but then see that there's nothing to do, right? Because 4 is already greater than 2. So the sorted portion maintains its sorted property. So next, we're going to say, all right, I'm now going to consider 5 to be part of my sorted section of the array. I see that, oh, in fact, it's, is still in its rightful place, so do nothing. Next pass is I'm considering the 1, and I see that 1 is definitely not in its rightful place amongst the sorted, if you will. So therefore, I should basically bubble it down to its rightful place, which is right here. Okay. And so the bubbling happens because we have the swap operation, and you might be thinking like, wait, why can't I just move it there? And yes, that's going to be one of the optimizations. But here in this non-adaptive version, we're relying on swaps similar to what we have for selection sort and bubble sort, which would mean that we will have to bubble it down to its rightful place using the swaps. All right, so then again, now my size of my sorted array is right here. So next time around, I'm going to look at 3 and then determine like, oh, okay, 3 amongst the sorted should be bubbled down to here. Okay, so that's insertion sort, or non-adaptive insertion sort. Let me pause here. Can everybody, or does anybody have a question between the difference or the difference between selection sort and insertion sort? Because that's often a source of confusion. Okay, so I just want to make sure if there are any questions, please post it. Okay. All right, so that's non-adaptive insertion sort, and no surprise, everything for the most part is n squared, right? You can end up having n squared number of swaps, right? Actually, it could behave as bad as bubble sort, if you will, right? With potential for having n squared number of swaps. If you did an average case analysis, I mean, again, still O of n squared, but it's like n squared divided by 4. Runtime only slightly sensitive to input, but what we're going to make it is much more adaptive, okay, by some of the optimizations that we're going to do. And the first one is, as I pointed out earlier, well, it seems kind of wasteful, right, to just do a bunch of swaps just to get the new element to its rightful position into the sorted section of the array, right? So let's do a move, right? So that means that we no longer have a swap right? And this if statement was basically used for the correct swapping of things. So we no longer need that. Now, we do need to keep track of the item that we're currently looking at. So we have item V, and which is the value at position I in the array. Okay. And whatever that, and now we've basically moved the declaration of the counter variable to up here. Okay. So now what this is going to do is the inner loop now is really going to find the position at which we should place the new element. That's what this if is doing inside of the inner loop. And once I find that position, I will keep track of it. And then I would basically move everything. And then make sure to place the element at the end once you've found what the correct placement for that element is. Okay. So of course, like as you're moving things along, if you get to the point where it's not less than the current element, then you basically found where that element should be inserted at. So you would break. Okay. But other than that, all you'll be doing is basically shifting, right? All the elements in order to make way for inserting the element in its correct position in line 12. Okay. So conceptually, it's the same thing. All we're doing is kind of, getting rid of swaps. Okay, that's the whole purpose of this optimization right here. Okay, now because we kind of moved item V and the declaration of the counting variable J to outside of the for loop, then we might as well make it into a while loop. Okay, and that way we can remove the break. Okay, and so now instead of the if for determining, so again we need that if to be able to identify the correct position where the element should be. We can just move that to be inside of the conditional for the while loop. Okay, it's just equivalent code for the most part. I wouldn't call it an optimization because it's either you do this comparison inside of here or you do it right here. So there's real no optimization there, but it's prettier, right? Because we don't have that ugly if in there. And so, right, decrementing the J here is analogous to what we had earlier, which was decrementing J here. Okay. And again, we need, once we're done finding its rightful position, we place it there. Okay. All right. Any questions? All right. So I have a couple of minutes left, so let me finish up with insertion sort. So insertion sort so far, if you look at the code, you'll see that we have this check right here in line 4. Okay. It's on every iteration of the while loop, I'm going to make that comparison whether J is greater than left. Okay, this is just checking whether the position that I'm looking to find, it's basically still in the proper range for the sorted portion of the array. That's what this is checking in line 4. Okay, so it basically makes sure that it doesn't go out of bounds. Okay, so we basically have this check or test that happens quite often, okay, as this while loop executes. But it's really seldom false, right? So most of the time it's going to be true. Okay? But I kind of still need it because otherwise it would introduce bugs into my code because I still need to make sure that J, as I decrement it, it's still within the range. I don't go out of bounds. Okay. So how do I fix that? Because it doesn't serve any purpose other than just checking bounds. But yet, again, every time this while loop is going to execute, it's going to make that check. All right, so here's where we're going to introduce this third improvement, which is the notion of the Sentinel. Okay, which sounds pretty fancy, but it is not. Okay, all we're going to do is kind of have a pre-processing operation, if you will, to find the minimum element inside of the array. That's what this does. Just find the min item or element. Okay? And you'd be like, well, why would I do that? Well, because if you place that element as your first element in the sorted section, then there's no point to have this check. Okay? Because you'll make sure that this comparison, okay, that you definitely need, which is the one that checks whether v is less than a at j minus 1, okay, is enough. That check would be enough, and you're always ensuring that you don't go past the left bound of the sorted portion of the array. Okay. And so we call that particular value a Sentinel, which is, again, quite fancy, but it's really just find a min, place it in its rightful position as the first element in the array, and then, of course, because we've done that first move of one element, then the rest of the outer loop needs to start at left plus 2, because we've already placed the correct element at the left position. Okay. And so that's that's the whole point of using the Sentinel value, is to eliminate this frequent check, because the fact that the minimum is that first element would ensure that I never get past the bounds, right? Because this while loop is at some point, this is definitely going to be true before we ever reach left, right? All right, so here's an example of using the Sentinel, right? I think it's the same, it may be a little bit different example, but here we have, this is our input. Oh, it is the same example right here. This is our input. So Sentinel, so this for loop right here, all it would do is iterate over every element, find that a Sentinel is 1, place it here, and then insertion sort would go about its business on the rest of the array, right? So in pass 1, it would look at this section of the array, find that, oh, sorry, that's not true. It won't look here. That's how selection sort always creeps in as you're explaining insertion sort, which is source of confusion. So it would not check the rest of the array. It would just check 4, right? And see that there's really nothing to do there, right? After I place 1, then the next pass will include 2, right here. So now this is the sorted section, which means that I would move the 2 to the second position and the 4 to the last position. Then again, it would and consider this section of the array, and then find that 5 is actually correctly placed, so there's nothing to do. Then lastly, it's going to consider the entirety of the array, and then move 3 to be placed at the position instead of 4, right? So part of this inner loop, it would remember 3, move 5 to the last place, move 4 to the next to last place, and then put the 3 in its rightful place. Okay. And that is the last optimization. And you might be like, whoa, but I am spending all that. Is it worth spending all that time to find the Sentinel? Yes, because you would do this only once, right? So this is a linear time operation, right? But you do it only once, okay? And then you got rid of those checks, those comparisons. Remember, those pesky comparisons is how we evaluate sorting algorithms. So the less comparisons you have, the better. Okay, but on the other hand, this kind of introduces, right, swaps. So it's a trade-off. So with these optimizations, with made, insertion, sort, adaptive is still on the order of n squared for worst case and average case. Best case is close to linear time. Okay, because so best case, again, assuming that, say, the input array is sorted, basically the outer loop's going to run and the inner loop is never going to run. So it basically boils down to linear time. Okay. Now, in terms of number of copies, n squared, okay, this is copies or effectively swaps, right? Same deal, n squared throughout. Best case is linear time. And because of the optimizations, is largely sensitive to input now. So the closer the input is to being sorted, the more, micro efficiency the algorithm has, because again, asymptotics don't change. All right, so I'll finish with this slide because we're running out of time. So advantages of adaptive insertion sorts, there is more efficient data manipulation, uses copying instead of swaps, right? And we kind of reintroduced swaps when we were finding the Sentinel, but again, that only happens once, right? So that is linear time, but it only happens once, and so we got rid of swaps inside of the inner loop. There's fewer comparisons, copies. The Sentinel key is the smallest key in the range. That's what we talked about. There is an overhead that I was just alluding to for that explicit first pass to find a Sentinel. Honestly, it kind of depends. I would say that if we were just sorting integers, finding the Sentinel is probably not worth it. But again, it depends on whether the comparison function is, let's say it's a hefty function, right? So for some reason, a comparison is more costly than a swap, right? That can happen. And if that's the case, then I might say, all right, I'll take that trade-off. I'd rather do more swaps by finding the Sentinel, but then reduce by far the number of comparisons by introducing the Sentinel at the beginning. So still O of n squared, okay? There's a nice thing where the algorithm is quite tunable, and in fact it is, out of the elementary sorts, is the most efficient to use on small values of n. And in fact, when we talk about insertion sort, if the array is small enough, intro sort, if the array is small enough, intro sort will fall back to insertion sort for small n. Okay. All right, so I'll stop it there in the interest of time. I think we're just missing counting sort, which we'll talk about on Tuesday, and then also talk about quicksort. Okay. But I think that would be all for today. Are there any final questions? Comparing is still faster than swapping. What constitutes a significant difference is hard to define, but yes, that is so. It really depends on the context, right? Whether a comparison is more costly than a swap, it really depends on that. For integers, definitely a comparison is way faster than a swap, right? For these example with integers, but in general, there are plenty of situations where a comparison is more costly than a swap, right? Say, for example, say that your struct that you're trying to sort contains a string that you need to use as your key to compare elements, right? And then an integer, which is the value that you want to sort, right? But in order to sort it, you need to rely on the key for the comparison. If you have that case, comparing strings can be quite costly, right? Whereas swapping integers, that's pretty fast. So that's an example in which you would want to reduce the number of comparisons and be okay with swaps. All right. Yes, we'll stop it there. Have a great weekend, everyone. Stay safe. We have office hours specifically for lecture questions, and we have the replay Q&A as well, if that fits your time. But please take advantage of those. I always feel kind of rushed in these lectures that are live on a stream as opposed to in person. So I'm sure I'm not getting to all your questions. So please take advantage of those Q&A. All right, and we'll continue on Tuesday.